So I want to compare prime elements and irreducible elements. Prime elements we introduced last time. An element in a ring is prime if the corresponding ideal is prime. So whenever a product is in the ideal, then one of them are. Remember? And this is same as saying that whenever P divides AB, then P divides A, or P divides B. That's the prime property. Irreducible elements are those elements that cannot be non-trivially fractored, which do not have a factorization. So here's the definition on the left-hand side. Let R be a commutative domain with 1. R star, remember, means the set of units of R. So these are all the elements of R that have an inverse in R, for which there is a V in R such that the product U times V is R. Yeah? So these are all the invertible elements of R, also called the units in R. A non-zero, non-unit element A is called an irreducible element. Probably we have given this definition before sometime. It's called an irreducible element if whenever you write A as a product of two elements U and V in R, then one of them must be a unit. So example, units in, irreducibles. Irreducibles in Z are plus minus primes, P a prime. I mean 2, 3, 5, 7, 11, etc., and then negatives. Irreducibles in Fx, where F is a field, are what we call the irreducible polynomials. Same in multiple variable actually. So for example, this polynomial in two variable polynomial with real coefficients is irreducible. You can check. Maybe this does require some work, but you can see that you cannot non-trivially factor it. Whereas this one is not irreducible if you consider it with complex coefficients. Not irreducible, because you can factor it non-trivially. Yeah. You could say that I can also factor this in this silly way. But we don't count that as a factorization. That's the point of the definition. You have to write it as a product of two non-units. Yeah. This one is a unit in real numbers. It has an inverse called half, which is a real number. Yeah, so this doesn't count as a factorization, but this one does count. All right. So that's the notion of an irreducible element. The result that we want to prove, and this would basically give us the main theorem in chapter 5. And we haven't really explicitly talked about chapter 5. Now when we look back, we'll see that we have actually done most of it already. Even more. So here's the lemma. Non-zero primes, a prime element. I don't know if I have to say non-zero. Probably prime elements were defined to be non-zero. Prime element in R is always irreducible. So prime elements are always irreducible. And if R is a PID, then the converse also holds. If R is a PID, then irreducible elements in R are prime. So that's why you see that in these two fundamental example of our principal ideal domains, the prime elements and the irreducible elements are exactly the same thing, the same set of elements. It's an illustration of this lemma. So maybe we should actually go through the proof of this carefully. So I'll remind you that an ideal is in another ideal if and only if the element, the generator of the smaller ideal is in the bigger ideal, if and only if B divides A. Right? Because saying this is same as saying this is same as saying that A is a multiple of B, so B divides A. Yeah, so these three equivalences you have to absolutely digest and use them interchangeably back and forth all the time. Okay, so let's go for this. Let P in R be a, so part A. So I am in a domain, okay? So in any commutative domain in R. Let's just write for emphasis, in a commutative domain. Be a prime element. And for emphasis, I'll say non-zero. Okay. What do I want to show? I want to show that it's irreducible. Means what? Means that when you write it as a product of two things, one of the factors is just a unit. So suppose I write P as a product of two things for some u v in R. I need to show one of these u or v is a unit. Now, u times v is just P, which is in the ideal generated by P. And since P is a prime element, this is a prime ideal. Since P is a prime ideal, that's what being a prime element means. Either u is in P or v is in the ideal P. So now if u is in the ideal generated by P, then you notice that u is P times something. So using this equation, you get P equal to P R V. And again, since we are in a domain and P is non-zero, since R is a domain, you can cancel P from both sides of this equation and you get R times V is 1. So V is a unit. And similarly, if V is in P, then you show exactly same argument that U is a unit. Yeah, so since either U is in P or V is in P, you get either V is a unit or U is a unit. Yeah, so this shows that A is irreducible. This is actually more straightforward. Part B requires a little more work. Let's see. So we are in a principal ideal domain now. So assume R is a PID, and then I take a irreducible element. I have to show that it's actually a prime element. Let P in R be a irreducible element. And I'm assuming this is a PID. How do I show something is a prime? I need to show that P is a prime. How do I show something is a prime? I take a product of two things that's in the ideal P, and I have to show that one of these things are. So suppose let A and B be two ring elements such that the product is in the ideal generated by P. And remember, I need to show either A is in P or B is in P. So here's the main tricky step. The key step is to consider, and these consider sentences are always where you have to think. The ideal generated by one of these elements A and P. Since R is a PID, what I get is that this ideal has a generator. So it can be written as all multiples of an element, some element x for some x in the ring. Okay. Then P is in this ideal. So P is in the ideal generated by x. So P is a multiple of x. Let's write it x times u for some u in R. Now I can use the fact that P is a reducible element. I've written P as a product of two things, so one of them have to be a unit. So either, since P is irreducible, either x is a unit or u is a unit. Let's take them in turn again. Guess 1, x is a unit. Assume. So if x is a unit, that means that 1 is a multiple of x. So 1 is in the ideal generated by x, which is the ideal generated by A and P. So 1 can be written as A times something. What's some letters that hasn't been used? C plus PD for some CD in R. So B is ABC plus PBD. And now you notice that AB is in the ideal generated by P up here. And P is in the ideal generated by P. So this term and that term are both multiples of P. So the whole thing is again multiples of P. So B is in the ideal generated by P. And now case 2, that's the easier case, where you assume U is a unit. But then X is PU inverse because P is XU. And because U is a unit, U inverse exists. So I can write X in here. And this is in the ideal generated by P because it's a multiple of P. But A is in the ideal generated by A and P, which is just X, which we just showed that X is in the ideal generated by P. So this is a subset of the ideal generated by P. So A is in the ideal generated by P in this case. What have we argued? We have argued that if AB is in parenthesis P, then either B is in parenthesis P or A is in parenthesis P. Yeah? Either X was a unit or U was a unit. If X is a unit, then B is in parenthesis P. And if U is a unit, then A was in parenthesis P. So we have shown that AB in P implies A in P or B in P. So P is a prime. Prime element. So next time we'll see what this means for this example, one variable polynomial ring over a field.